No, record, sorry. All right.
Okay, this is better, isn't it?
Yeah, perfect.
Okay, excellent. Okay, thank you, Yuki, for the introduction. As Yuki said, today I'm going to talk about deep learning together, or the impact of deep learning on 3D geometry. In fact, how we can learn 3D geometry. This is going to be about three-dimensional computer vision and, of course, learning. So you probably, I think, have seen the problem of supervised and unsupervised learning before with Yuki, but just as a reminder. So this is not 3D vision yet, but this is a typical problem, a typical setup of a problem that we might want to solve in computer vision. So suppose that our task is to label those images with concepts. So what this means is that for each pixel in each image, we want to tell whether that pixel, say, is a person, is ground, is sky, etc. Right? So this is a segmentation problem. Now, the way you do it normally is through supervised learning. So this means that you design a deep network that can solve the problem. And then to learn this deep network, you use a supervised training data set. So this data set is essentially just what I show here in the slide. So it's a bunch of images like those, generally obtained cheaply by downloading them from the internet. And together with those, you also have label maps like those ones. And these are obtained essentially manually. So this is very expensive, as you can imagine. But at least until recently, it was necessary to get good performance on this sort of task, where the goal is to give a semantic interpretation of the content of an image. Okay. But because getting images is relatively cheap, but getting labels is actually very expensive because, again, you have to do that manually. Ideally, what we would like to do is to be in a situation where that part of the story is removed. So we only have images without having any manually provided supervision. So somehow, just by looking at the images or maybe some metadata that we get for free, we are able to learn to solve a similar task. So this is unsupervised learning. Now, supervised learning is something which is very powerful and has been developing quite tremendously in the past couple of years. But most of it has been about the problem of semantic interpretation. For example, computing image representation that would be useful for classifying images, segmenting them, okay? But today I want to give you a slightly different interpretation or perspective on this story. So we're still gonna look at methods that can learn from data without supervision. That's gonna be a leitmotif here. But instead of looking at semantic interpretations, we're gonna look at geometry instead, okay? So what's the motivation for looking at geometry instead of you looking at semantics directly? So this is a bit of a illustration of what computer vision really is. So in vision, at least for the past 20 years, we've been focusing on the right part here of the figure. So vision effectively is a sensor. So it's a device that can measure light. And we have been preoccupied with the artifact that is produced, which is an image, okay? And trying to come up with a relatively simple interpretation of the image content directly. For example, labeling each pixel with a semantic class. So here, the fundamental unit of analysis is an image. And the goal of computer vision is to try to attach, I'd say, some relatively superficial semantic or meaning to what you see in the image. But really, the image is just a reflection of the natural world, right? The natural world is very complex. There's much more than what can be captured in a single image. And in a certain sense, what you want to do through vision is not so much describing what you see in the image, but rather obtaining information about the world which is contained in the image. Now, to do that, you need to be able to describe what the world is, right? So you need to have a model of the world. And this essentially is the fundamental problem of computer vision, more so than doing the imaging part. I'd say what's really complicated, really complex, really difficult to achieve is modeling the natural world in a way which is suitable for learning, okay? Now, there is an interesting thing about the world, right? That's the same for different intelligence, different type of intelligences. So for example, here, this is a slide that you have to take with a pinch of salt, but suppose you wanted to talk to an alien, all right? So the alien will live in the same universe as you do, presumably, although I come from a very, very far away world. But the basic units that make up the universe, as far as we know, they're the same, right? there are some elements like space, time, materials, matter that do not change, whether it's me looking at them or interacting with them, it's an alien that does that, or it's just an animal, right? So in a certain sense, these are the fundamental components of the world. And therefore, if you really want to have models of the world that are suitable for learning, we should not ignore these factors. So we cannot ignore space, two-dimensional space. We cannot ignore time. We cannot ignore materials and physics in general. But this is actually what happened in computer vision in the past 20 years, since we have been starting to use machine learning. With machine learning, we're taking a shortcut in which we look at the semantics of, which is carried at a superficial level in the images themselves, but we have essentially neglected to try to model what's actually out there in the world in terms of space, time, materials, etc. So this brings me to the topic of geometry finally. So geometry is a very interesting thing to study because, of course, is the language in which you can start to describe the three-dimensional world, okay? So geometry effectively is something that practically all animals that interact with the world in any sort of complex way have to understand at least at some sort of intuitive level, okay? And there is more. So the understanding that I have of geometry, at least the intuitive understanding that I have of geometry, or the geometry of the world, is actually going to be probably very similar to the understanding that a cat or a dog might have, all right? Of course, I also have a mathematical model of what geometry is, and we're going to discuss that. But at an intuitive level, as just an agent in the world, probably the way my brain looks at geometry and thinks about it is not all that different. Now, what this suggests also that in order to understand geometry and to learn it from data, we do not require very high abstract and sophisticated abstractions, as we might actually need for understanding concepts like the semantics of regions in an image. For example, understanding what a cardinal bird is, what a person is, and what a specific type of building is, right? So these are tasks that we very often solve in vision, but they require to have access to a library of concepts, which are very abstract. And to access those concepts, essentially, I cannot do that without some form of human-provided supervision, because these are concepts that effectively depend on human culture. So these are human artifacts. And if I want to infuse them in my learning, in my learned model, then I have to establish a connection between the human world and the machine, which usually is obtained through supervision. On the other hand, with geometry, because geometry is so much more basic and low level and so necessary for all sorts of agents to function, then there is a much higher degree of hope that we may be able to learn about geometry from vision or using agents without having to pass human provided semantics or supervision to them. So we're going to start by giving you a little example of what I mean by that. Just from a paper that we did now quite a few years ago. So now what we're going to look at is the problem of reconstructing a three-dimensional object purely from images. Okay, so the task that I'm going to solve here is, given a collection of images without labels, or human-provided labels, I want to be able to tell what's the shape of the stuff which is contained in those images. Okay, I want to learn to do that from a single image, if I can. Now, if you look at what happened until recently, people were looking at this problem and trying to solve it using a number of hints or contribution in terms of labeling that would come from some external provider of labels information external to the agent or to the machine that would actually learn from data. So it was not just about images, but it would also need to provide with the images some hints about the shape of the object that you could see in those images, at least some vague model that you could then refine from the images. You might need to have multiple views instead of just a single image at a time. You might need to have depth maps that you can usually obtain with LiDARs or other special instruments, but generally speaking, you don't have access to those. Silhouettes, key points, etc. So we wanted to get rid of all of that, okay, and trying to learn the shape of objects from images without any supervision. Okay, so again, geometry from raw data without supervision. So this is an example of the data, how it looks like. So for example, suppose we focus on cat faces as a theme. That's the training data, so just random images of cat faces that we got from the internet. And then there is a process that looks at those images and learns to reconstruct from one image at a time by itself using a predictor, the possible shape of that object. And it tends to work quite well. So the way this worked was by using a notion of symmetry of the objects. Okay, so we're making a little assumption on what kind of object we could be looking at. So we were assuming that those would be symmetric. Symmetric means bilaterally symmetric. So most animals have a symmetry, right? So that would cover that class of objects. But in fact, if you look around you, many man-made objects or other objects you can find in nature, they would have some form of symmetry. Okay, and you can use the fact that the shape of the object is symmetric to provide additional constraints for the reconstruction and simplify the task. So the way we approached the problem at the time, and we're gonna work on extension on this model in the remaining 2 hours in a way or another, was by designing what I call here a photogeometric autoencoder. So you probably have seen already an autoencoder, but if not, that's essentially a pair of functions, one which takes the input data, in this case an image, and estimates some sort of code or representation of the data. And then there is another function that takes that code or representation and goes back to the image by decoding it. All right, and then you can close the loop for training. So in this case, the encoder is, or the autoencoder is photogeometric. It means that the code that is being estimated has a meaning that is grounded on geometry and the physics of light and color, etc. All right. So in particular, what we have here is an input image, and we have a certain number of neural networks which are trained in parallel, which estimated the viewpoint. So where is the camera that's looking at that image? So in this case, for example, that face is looking slightly to the left. Okay. Then you have a depth map, which is simply the distance of each pixel or the point that the physical point that projects onto each pixel from the camera plane. So that's just the depth of what you see in the image. Or I shouldn't say that, it's just a depth map which describes the object that you see in the image, but it's not actually what you see in the image directly. And you also have a texture, which is just essentially the color of what you get there. All right. And you can take these three ingredients. You can take the viewpoint, you can take the depth that describes it to the geometry, and you can take the texture, and you can combine them in a box, which is a differentiable renderer. That's just a differentiable function that takes these three ingredients and reconstructs the image based on those. Okay, so you get an image I hat here, which should be a good approximation of the image I. So you can close the loop there with a reconstruction loss. You can use just the L2 distance between the corresponding pixels. Okay, and you can try to optimize that. And it means learning the network, these three networks here. Excuse me. The renderer, by the way, is handcrafted. So that's just a bunch of rules that map the photometric and geometric information we have extracted with the network back to an image. So this is known, this is handcrafted, it's chosen by me based on knowledge of how geometry works and how photometry works, okay? But the rest, the model, the network that actually does the estimate, we can try to train from data by simply observing lots of input faces and try to reconstruct all of them, okay? Minimizing that reconstruction error. If you try to do that, that doesn't really work. So what you get is that the depth you estimate is completely flat, all right? Just like a plane. The viewpoint is straight on, all right? And then the entire input image is transformed verbatim onto the texture, okay? So this is essentially what we call a degenerate solution. It's a plausible solution. It's just essentially what you reconstruct is a photo of the input image, right? So it's something flat that happens to have painted on top of it, on its surface, exactly the right colors in such a way that when you render it, when you look at this photo, then you get back your input image. Now, this is a valid solution, all right? This is perfectly valid geometrically, photometrically. It's just not the solution I want, okay? So what I need to do, what I want to do here is to try to remove from the possible space of solutions, this sort of degenerate solutions. And this is where the symmetry becomes important. So what we do here is we're going to enforce that the depth map here, the 3 geometry, and the texture, the albedo, I'm going to see in a minute, is actually symmetric by the vertical axis that are drawn here onto those 2 images. Okay, so it means that if you flip this left and right, and if you flip that left and right, approximately those things should not change. They are invariant to flip. It means that the object is symmetric. All right. So if you do that, then it turns out that what you get is a reconstruction with this, which is not degenerate any longer. Okay. So if you don't impose this structure that the object should be symmetric, you get a general solution usually. If you do impose the structure that the object is actually symmetric, then this goes away. Why is that? Well, typically speaking, if you assume that there is symmetry in your object, then one image is essentially worth two images, okay? Because you can flip the image, and this is as if you were looking at the same object from the other side, effectively. So because of this notion, effectively looking at a single image is close to observing two, and from two, then a lot of the geometric ambiguity goes away, and we can reconstruct the object. Okay, that's intuition. Now, there are many ways in which you can implement that. The particular way we've chosen to impose symmetry here was a nice trick that you can probably find this to be useful in other problems as well. So what we do is we flip a coin with a certain probability, 50%. We take whatever output this encoder-decoder network produces, so this would be the depth map, and with 50% probability, again, we flip it left to right. And the same we do here for the albedo, okay? Now, because, and the viewpoint does not change, because this is this flipping happens randomly, then the only way the model has to guarantee that regardless of how the coin is flipped, the reconstruction is about the same, is to make these two reconstructions symmetric. Because if they are symmetric, it does not matter how I select my coin, then the reconstruction, the depth would be the same, because even if I flip it, due to symmetry, it would be unchanged. Okay. So this is a nice trick that you can use in many other problems as well. If you want to impose some constraints in your data, you can try to perturb it in such a way that the data would be corrupted unless it has the property you want, in this case, symmetry, right? And this is actually sometimes better than trying to impose these additional constraints as further training losses. For example, that avoids having to choose how to balance the additional training terms that you get in the loss. So you do that, you get symmetric reconstruction. Now, in practice, you will notice that the face is not exactly symmetric. For example, you have a bit of hair here. The lighting is also not symmetric because the light will come preferentially from one direction. So what we do is we make the model a little bit more sophisticated. So we also estimate lighting and albedo. So this would be the texture minus the lighting. Combining the depth, the lighting, the albedo, combining the depth map, which is the 3D shape of the object, and lighting give us the shading. And combining the shading together with the texture, I can reconstruct, so taking the albedo, the texture together with the shading, gives me the shaded version of the texture. And combining that with the depth and the viewpoint gives me the final image. So I can close the loop and train my photogeometric autoencoder. Okay, so that was the idea at the time. Now, you will also notice that not all the bits and pieces are symmetric also in terms of the actual shape, for example, because of the hair. So far we'll only dealt with the no-symmetry, which is due to the lighting. So how do we handle that? Well, we estimate on the fly together with yet another network as a confidence map that essentially tells us which pixels are likely to be in correspondence of points in the physical object, which are very likely to be symmetric, and which ones are likely to correspond to points that are not symmetric instead, okay? And this is trained automatically together with the other parameters without having to deduce an additional balancing term. So you do that, and what you get is that you can get, sorry, this is just an animation. Probably it's gonna stop now. Right, so these are some of the results we got at the time. So you can reconstruct these faces again from single images, and they reconstruct quite nicely. But what was particularly nice is that because the model trains properly, then it tends to generalize well. So now if you apply it to these images here that are, of course, not real faces, and the model only sees real faces during training, you can still get some reconstruction, which, they're not perfect, but they're kind of sensible. For example, you can see here the reconstruction of the emoji. So you get this sort of very strange crossover between a real face and an emoji. But the 3D shape resembles what you get in the input a little bit, right? This really shows that the model is capable of achieving a quite strong degree of generalization, which is a really good sign, I think. And of course, you can work on other things other than human faces, for example, cat faces. All right, so that was my fairly long introduction to the topic of unsupervised learning using geometry, or supervised learning of geometry. Now, the next 20 minutes or so, I'm going to discuss a particular class of models, which are called radiance fields. So these are the modern way of doing some of the stuff I just described, with usually obtaining usually much greater visual fidelity. Okay, so I'm going to show you first a couple of results of this model, and then I'm going to show you how this works. So these are some reconstruction that you get from NERF. Okay, so what I'm showing here, they look like synthetic models. They are actually. So the training data was generated from synthetic models, but what you see here are not the synthetic models themselves. These are reconstruction of those three-dimensional objects from a deep network, okay, that was trained to generate those images or to understand what is the color and shape of those objects. So they're basically indistinguishable from what we get from computer graphics, which basically means that this network has learned to reproduce with very high fidelity the geometry and shape of the objects themselves. Okay, so that's our goal. Our goal is to learn a model, a network, that can produce images of that quality. So to do that, I need to describe a little bit how image formation works, how you get the image to depend on the geometry and photometry of the scene, all right? So the image is formed essentially by the interaction of your eye and the light that in turn is emitted from the scene, all right? So here you have a scene, some matter, in this case is a translucent medium, and I didn't choose that at random. There will be a reason why this is not completely opaque, all right? And, you know, so my light, there are light sources in the scene. Light bounces off different surfaces and is transmitted and is absorbed by different materials in very complex ways, but eventually some of this light will escape from the scene and will enter my camera or my eye and form an image, okay? So I just sample those photons that enter my eye, which of course are the result of this complex interaction between the light emitted by light sources and the matter, the material that exists in the scene. Now, to study this phenomenon, I'm going to use radiometry, which is a simplified model of light-matter interaction. And of that simplified model, I'm going to show you an even more simplified version, okay? Because there isn't no time to cover this in any level of depth today. But I'm going to give you a few elements at least so you understand what's going on. So the first question is, how do you measure light, all right? So we know that light is an electric magnetic phenomenon, but at the level that is required for understanding the next couple of slides, just imagine that light is a bunch of photons that travel through space, or if you like, a wave of electromagnetic energy that goes from left to right. And this wave, in this case, is going to be planar. It means that at different points in space, along the planes here, I get the same amount of energy flowing through, all right? The same characteristic and properties. So this wave, or the characteristic of the photons going through these planes is going to be invariant, regardless of where I position myself on the plane. Okay, so planar wave. Now, what I'm going to do is I'm going to measure the luminous flux. So I'm going to denote that as phi x. So what is luminous flux? Well, it's simply the amount of power that the light is carrying through a small element of, or chosen element of a chosen surface in space. So in this case, the chosen surface is A, that has a little disk that has a normal n, all right? And phi x is going to be the amount of light energy that essentially flows through this little surface element, which happens to be located at location x along this line, all right? So I have y and z along the other two directions, which are not shown here, and x is the direction of propagation of the wave or the photons. Phi x is just the amount of energy that flows through. So the first thing to notice is that if the stuff in between two surfaces like those is completely transparent, and if the light goes through is a planar wave, so the photons go in a parallel direction effectively, then the amount of flux or energy that I observe in this location or through this surface is going to be the same as the amount of energy or flux that I measure through that surface. So that's not going to change. It's going to be invariant. But usually we're not so lucky. So usually there is stuff in the world, right? Well, I suppose it's lucky that there is stuff, otherwise this would not be very interesting. Materials in general, they have a property that they can absorb light. They may absorb light completely or generally just in part. So we're going to look at the case in which materials are translucent. It means that they absorb light partially, all right? Or the special case completely. So we're going to look at thickness of material, dx, here along this axis that is being, along this element of the x direction or x-axis, which is the direction of propagation of the wave. So that's going to be the thickness of the material, dx. I'm going to have an absorption coefficient, sigma x. This is also known as occupancy or opacity sometime. And sigma x by dx is defined to be the fraction of luminous flux or power, which is observed within this volume, all right? So that means that 1 minus that fraction is going to be the amount of power which is being transmitted. That means, in turn, that if phi x is the amount of power I get at the start of the volume, at the start of the thickness of material, then the amount of power I get at phi x plus delta x, or dx, is going to be this number multiplied by this coefficient, 1 minus sigma x dx. Okay, that's the amount of power that is being lost because luminous energy is being absorbed by the material in the thickness dx. Now, what I'm going to do, of course, is I'm going to take this to the limit of dx becoming infinitesimally small. So what I get here by just rearranging the terms and dividing by dx and taking the limit is that the derivative of the luminous flux along x is going to be equal to minus the absorption coefficient multiplied by the luminous flux itself, phi x. So you recognize this as a simple differential equation whose solution is given by this integral here. So you're going to have that the amount. So if you have a certain amount of flux phi x1 here, and you want to measure how much flux remains at phi x2 here, going through all these little slices of material, each one of them absorbing light in a different manner, then the way you do that is by taking the flux you have at the input and multiplying that by this coefficient, which is the exponential of minus the integral of the absorption coefficient in this volume, okay, on this thickness. So that's absorption. So that's how light is being absorbed. But of course, I also need light to be emitted. Otherwise, there is no light to be observed. So there is no image. So we're also going to make the assumption that each thickness of material, in addition of being able to absorb light, can also emit light of its own. Basically, it's like a lamp, a lighting bulb, a light bulb. Okay. Again, I'm going to have a thickness of material dx. Epsilon x is going to be the emission coefficient, and the amount of flux or power emitted within this little volume here is going to be epsilon x dx. All right. So if phi x is the flux before I get into this volume, at the end of it, my flux x plus dx is going to be incremented by the amount of power emitted, which is epsilon x dx. So this is what you get here. Okay. So now we know how light is absorbed by material and how light is emitted by material. All right. Of course, now I have to combine these two notions. So I'm going to assume that there is a little bit of light which is emitted by this section of the material, which is a thickness dx again, and then I'm going to call x the point where I measure them on this luminous flux, which is generated within this little slice, and then I'm going to measure how much power remains here. So what I need to do is to get the amount of flux emitted by this little guy, and multiply that by my absorption coefficient, which, as we've seen before, is going to be the exponential of this particular integral of the absorption coefficient within this element of volume. Okay. So what this means is that the amount of luminous energy I see at the output here is going to be given by the amount of energy which is produced within this little slice multiplied by the coefficient, just like that. And of course, the more complex and complete situation is in which each element of the material has a chance of emitting light, but also of absorbing light that came before it to, in this case, from the left, right? Now, each one of these slices can emit light, and it will also absorb a certain fraction of light that comes from left to right, okay? And now, if you want to get the total amount of energy or luminous flux you see at the output here, well, you need just integrate what I showed in the previous slide throughout the entirety of of your material, and that's the expression you're going to get. So this is simply the integral of what I had in the slide before, just done assuming that each one of the slices can now emit light. All right, so this is the total amount of luminous flux I get at the end, assuming that the material can absorb and emit light in the manner just described. Now, I'm going to use a normalized variant of this equation. So what I'm going to do is going to rewrite the amount, the luminous flux at the end here as the integral of, well, these two quantities, Cx and W. This is really a function of x, but for clarity, I denoted that as x goes into x2. So what does that mean? So Cx is essentially the color of the light. And I'm going to make the assumption, although that's not physically motivated, is mathematically convenient, that the amount of energy emitted by the material is proportional or is given by the product of Cx, which is just a function I define now in a sort of arbitrary fashion, and sigma x, which is the absorption coefficient of that element of material. All right, this is again not physical, but it's useful because it leads me to a simplified equation here, in which Cx is this function that I'm going to learn later with a deep network. Okay, and Wx into x2 is essentially what was before the absorption that you would measure from x, an arbitrary point in the volume, down to the end, x2. So that's why this goes from x to x2. That's the amount of light absorbed here, but renormalized. All right, renormalized to account for the fact that I've decomposed epsilon in this manner. And the nice thing about that is that because of this renormalization, now this function W becomes a probability density. It means that if you do take the integral of W from minus infinity to x2, then that sums to 1. All right. In other words, this is to say that the amount of light I measured at the end here, where my eye is going to be a weighted combination of this function Cx, which describes the color of each one of these elements of matter in 3D space, integrated along the direction propagation of light, okay, and weighted by this function W, which is a normalized function of what? Of the occupancy, of or opacity or absorption coefficient that also characterizes my material. Okay, so that's how you get interaction between the color, the geometry, which is captured by the occupancy of material absorption, and if when you combine these ingredients together, then you can get an equation for the light you observe. Now, I described this in the continuous case, but of course, in practice, we're going to discretize that because that allows us to simplify implementation of deep network. So before I had integrals, and now I'm going to replace those by summations. For example, the amount of light I measure at the end of the volume, which is again what gets into my eye in practice, is going to be a summation over points xi. These points xi are nothing but samples along the ray, which is the direction of propagation of the light. And each one of them, they will be equally sampled, equally spaced usually. And each one of them will represent a little section of that material. And, you know, I'm going to assume that within each section, the absorption and the color stay constant. So if you do that, then this integral becomes just a summation, and the expression for the weighting function W also involves computing a summation over these discrete elements of discretized version of the volume I described before. Okay, so that's how it discretizes equations. Now, what's the interpretation of that? Well, so this is my eye or my camera, and what I want to determine is the amount of light, the amount of luminous energy which is received by an element in my sensor, to be the retina or the CCD in the camera. And I'm gonna look through, so what is the light which is received here? Well, that's the light that comes from the scene into my eye, right? Through a particular direction. The direction is a function of which pixel I look at, which element in the retina I look at. But given a particular pixel, then the pixel will receive light that goes through the scene into my eye along a specific direction, which is also called the marching direction, all right? Now, intuitively speaking, what my eye is going to see is not something which is behind the object, but something which is in front of the object. Why is that the case? because the material will either completely or partially absorb light. So if there is light which is emitted at the back here, by the time it gets into your eye, it's going to be almost completely or entirely absorbed by whatever is the material in between. What you're going to see is actually the light which is emitted closer to your eye, basically on the side of the object, which is closer to you, which is not occluded. And so if you look at the function W, which is the probability, which was that weighting function that decides the color that you measure in your eye, how that depends on the color of the volume element that exists in space. Well, this function W, which does the weighting, is going to tell you that the important samples or the important points are the ones that are close, where there is an object, because just air does not emit light by itself. So there has to be an object, but not the entire object, only the portion of the object which is not occluded by something else, all right, by itself, in fact. So it's going to look something like this. Now, what this practice means is that in order to determine the light here, you can go from the eye back into the scene, work out which is the value of the function W, right? And after the function W has found an intersection with your scene by saying that which you can determine by the fact that the weight of those portions of space would be large, then after that, the function W has to taper off. And so you know that all this contribution can be essentially ignored because they are not visible from this particular viewpoint. That light just doesn't get into your eye, okay? So that's why we normally, when we write random equations, we start labeling points not from the direction of propagation of the light, which could be from left to right. So, it would be natural to say this is x0, this is x1, this is x2, but rather you label points the other way around. So you say this one is x0, this one is x1, this one is x2. So the points are scanned or labeled in the direction which is opposite to the direction of propagation of light, okay? Again, the reason is that this has become more natural. When you look at the rendering equation, you realize that everything which is down here will usually not contribute very much to the light which is got by your eye because of self-occlusion. And so once you do that, then you can rewrite your rendering equations like so. So phi sensor, again, is the amount of light received by a particular pixel. That is a weighted combination of the color that different elements, different bits of materials have in space, sample of these two-dimensional points, okay? And W is the weighting function I discussed. Now, of course, this is only for, so far we only discussed energy as if it was a scalar quantity. In fact, the light is composed of different frequencies. So you have a whole spectrum of different energy levels of different frequencies. For the purpose of normal imaging applications where we're using standard cameras, we're going to measure 3 bands of colors, red, green, and blue. So each one of them essentially is a measurement of the luminal flux restricted to a specific band of frequencies. This doesn't matter too much for the rest of the discussion, but just to say that you could actually add additional color channels, this would be physically meaningful. It's just that consumer cameras, which is the ones we use to capture data, only measure 3 different bands. So we limit ourselves to modeling those bands, so red, green, and blue. Which just basically just means that C, that before was a scalar, now is a vector that has 3 elements, one for each one of these 3 colors. There's one more detail. So when you look at the bit of material, so far I pretended that everything was just going through a straight line, right? And light, so light was propagating through planar waves, but that's actually not normally the case. In particular, one thing which is interesting and actually important to model to get high quality results is the fact that the material's appearance, the color of the material, will kind of depend strongly, at least for some materials, or should say for most materials in practice, on the viewing direction. For example, if you look at this cloth or textile here, you'll notice that the color of the brightness of the light which is emitted by a given element of the material will depend on the orientation or the direction in which you observe that element of material, depending, for example, on the reflection. Okay, so that means that if you look at different direction, the same element of material will emit different colors. And to model that, what I'm going to do is going to extend the function C to depend not only on space, all right? Not only which particular point in space I look at, but also on the direction R, which tells me from which direction or I'm looking at that element of material, which is the vantage point. Okay, so that allows me to model this sort of effects or visual effects which are view dependent. Now, finally, just very briefly, what I described so far as again a simplified case in which waves are planar. This is not generally the case. So normally in radiometry, you do not just measure luminous flux, but you measure is another quantity, which is radiance. Yeah, that's why this is called radiometry in a way. Or that is to say, radiance is probably the most important quantity in radiometry. This is similar to luminous flux, but it's normalized in a different way. So it's first of all, it's view dependent or direction dependent, as you said. And also, instead of normalizing through measuring the density of luminous energy that goes through this sort of circular sections, what I do is, or what you would do is to measure the density in the unit of solid angle. Okay, basically the size of the cone of light you're observing. But this is too much detail for today. So, but if you're interested in understanding this properly, you would have to look at the notion of radiance and figure out how this works. So what is a radiance field? Well, a radiance field, which is actually what I'm going to model with networks, is just a pair of functions. The first function is C. That depends on two quantities, X, which is a point in space, and R, which is the viewing direction. And C is just a three-dimensional vector, which is the color of that element of that point in space. All right. And the other thing you need is sigma X, which is the absorption coefficient, again, sometimes called also opacity or occupancy, which tells you how opaque that particular point is. Okay, given these two functions, sigma and C, then you can generate an image. How do you generate an image? Well, for each pixel U, you're going to march along the ray, and you're going to compute the integral I described before, or in practice, you're going to do a discrete version of that, just a summation. So in other words, the color of pixel the pixel U here, so the value IU is a three-dimensional vector, three numbers RGB, which is obtained by averaging the color along this ray, weighted by this corresponding weighting function. Okay. All right. Now, what's going to be interesting here is how to get those two functions. All right. So now we have said that we can capture the scene in two functions, and given those two functions, we can generate any image of the scene by simply sampling different rays, okay, and measuring those integrals or computing those integrals. But the question is, how do I model those functions? Well, I'm going to use networks to do that, and then I need to train those networks. So the way this is going to work is I'm going to take a bunch of training images, a certain number of them, typically hundreds, okay? I'm going to we're going to formulate or implement the two functions sigma and C as MLPs or some other kind of deep network. I'm going to generate the image that I get from these two MLPs back. So I'm going to get I hats, which is obtained by doing ray casting based on the function that I got. And Ri and Ti here are just the rotation translation of the camera. So what the image it generates is going to be view dependent. So it will depend on the location of the camera in 3D space. I'm going to get an image here, and then I'm going to compare these two. And they're going to try to minimize the error, the construction error of the measure, which is just the two distance between the reconstructed image and the ground truth image. Okay, so that's the idea. So then I'm going to just use gradient descent as normal to try to train this network that solves this task of fitting those functions. Okay. So there's one more thing you need to know. So what's the nature of the functions, or what's the nature of the network that I'm going to implement? Well, there are different ways you can do that. The one which was introduced by this very important paper, which is called NERF here, which stands for Neural Radiance Fields, was to use MLPs, multi-layer perceptrons, to implement the functions sigma and C, all right? So this function here, literally, they're just MLPs. That's the most basic kind deep networking you can think of. But crucially, and that was a major innovation in this paper, instead of feeding the three-dimensional point X directly, all right, which would make this not work very well, you pre-code or encode this point using this function here, which is called SPENC, or spatial encoder, that takes a scalar A, all right? And in fact, in the case of three-dimensional point, it's going to be three scalars. X, Y, Z, and returns a copy of that, as well as versions of the same number, which are obtained by passing that number through sinusoid, sine and cos, so sinusoidal functions, multiply by a given scalar here, which is a multiple of 2. So what this does effectively gives you some sort of Fourier encoding, roughly speaking, of the position of the point in space. Okay, but that's it. That's the definition of a spatial encoder. It's very, very simple. If you do that, then this actually starts to work very well. Now we can look at the detail of this model a little bit further. So again, we have X here, which is a 3-dimensional point. We have the spatial encoder where you set K to 10. So that means you have 21 components here multiplied by 3, so 63 numbers. Why 21? Because K is the number of frequencies you use. You get 2 numbers per frequency, plus you have the DC component, which is just a copy of the input. Okay, sorry, that's not the DC component, that's just a copy of the input. All right, so each one of these elements is decoded into 21 numbers, and you have 3 of them, so 63. And then you have a certain number of perceptual layers here. So in this case, you would have 4, and the determinate features have a dimension 256 in this case. All right, so this is basically a detailed version, a detailed view of the architecture, how it looks like. So for X, then you get spatial encoder, then you have 4 MLPs here. This is a concatenation of the spatial encoder again. This is almost like a residual connection, all right? Not quite, but similar. And then you get 4 more layers of MLP, and then a linear layer that eventually gives you back sigma X, all right? For the color depends both on X and on R. So X is 3D point and R is the viewing direction. So this works very similarly. So we reuse part of the network that we use for encoding the occupancy here, or the absorption here. But then out of that, you add also information about the viewing direction, also through coded up using spatial encoder. And then you have another MLP that does the decoding into the final color, all right? Now, the reason why I highlighted all the dimensions here and all the sizes of the parameters throughout the model. So for example, this MLP has a number of parameters, which takes 256 kilobytes of memory to store. It's just to show you that the overall amount of memory you require to store the entire scene is just 5 megabytes. Okay, this is a tiny model. It's a tiny model that is going to code up for lots of images. So this is actually great. And so these models, they achieve a tremendous amount of compression of the input data, because the input data is just different views of the same object, and intuitively speaking, they're highly redundant. Now, these models, the great strength of them is the ability of summarizing that information in a small number of parameters. In fact, the amount of information or data which is required to store the model is going to be far less than the amount of information that you require to save the images on disk. All right, so truly, this is compressing the data in a very, mundane sense, just number of kilobytes. Now, this works and can generate results which are very high quality, but has some drawbacks. One of them is the speed, right? So the issue with this model is that for each time you want to render a scene, you need to take every pixel you need to cast a ray. For every ray, you're going to get a certain number of 3-dimensional points. And for each one of these 3-dimensional points, you need to evaluate your MLP to get the value of the color and the value of the occupancy. And this is just slow, all right? The MLP is not a large MLP, but you need to evaluate it millions of times for each image you render. So it can take minutes to render that, and it takes even longer to train. So I'm going to describe briefly variants of NeRF that allow you to at least speed up tremendously training as well as evaluation, all right? So the most obvious thing is to ask, do we really need an MLP? All right. Can we represent the function sigma s and s of x in a different way? For example, can we just represent that with a volume? So what this means is that instead of implementing sigma x and cx with an MLP, what I'm going to do is I'm going to simply tabulate the value, obtaining what is known sometimes as a voxel grid, a voxel space. Okay. So I can do that. In fact, this was done by authors last year. The first paper I've shown that has tried to do that in the context of NeRF was direct voxel grid. And that's all they do. So they just tabulated the function sigma x and the function cx as well. for that, I think they also have an option of using a small MLP on top, but basically is the same idea as before, except that instead of having an MLP to produce those functions, we just store them brute force in a table, all right? There is a little bit more, so it's not completely trivial. For example, what these authors figured out was important is the way you interpolate the information in the grid. So the grid will have a finite number of voxel elements, and you generally want to be able to sample that function at arbitrary points in space, so you need some interpolation. The way you do the interpolation is also important. In practice, you use linear interpolation, which is very simple, but you need to do that before you apply certain other nonlinearities in the model. So basically what I said is basically a table with some details that make this work better, okay? If you do that, the advantage is that if you train NERF in the way it's got before, it might take, say, 30 or 40 hours on a good GPU for a typical scene. If you use this direct voxel grid idea and optimize that instead, then it takes maybe 20 minutes. So it's order of magnitude faster. The drawback, though, is the size. So NERF is a very small model, so 5 megabytes that captures your scene. But this thing here, because it's tabulating these volumetric functions, is actually expensive in terms of the amount of memory that it takes to store the functions. So it's going to be 0.5 gigabyte. Okay. So trade-off speed for size. So one more idea I want to tell you before the break, which is called tensor RF. There are a bunch of these now that work in a similar manner. They're really nice and really elegant solution to this problem. So you're still the idea is still to have a grid, so you get the speed. But instead of storing the grid completely, what you do is you store a low rank decomposition of that grid. It's kind of like doing PCA of this data, but not quite, but very similar. So what this means is, in order to represent this grid, you can represent that as the product of an image-like structure together with a vector-like structure, where the image is defined along two spatial dimensions, x and y, and the vector-like structure is defined along the other spatial dimension, z. So to get the value of an element in the grid here, what you do is you read off the corresponding element in the plane, the corresponding element in the vector, multiply them together in a certain way, and that gives you the value you want to use. Now, in practice, this is a little bit more sophisticated. So you repeat this composition 3 times, placing the image along different coordinate axes. So you have 3 options there. So this reconstruction is repeated 3 times and averaged. In addition to that, these ones are not just images or vectors, but each one of those cells contains a certain number of elements. So this is basically a feature vector. And when you do the multiplication, it's not a scalar multiplication, it's a multiplication on these local code vectors. Doesn't matter, it's basically the same idea. At the end of the day, what it turns out, what you achieve is that you can take this scalar function, for example, the occupancy or the absorption, and decompose that as this product of 2D and 1D functions that are not scalar, but have a very small number of components. So by the time you do the math, then you realize that you're saving tons of memory by doing so. And you still have the advantage that evaluating an element of the grid is not quite as fast as just looking it up as was before, but reconstructing the value of that element is much faster than running an MLP. So you get both the speed as well as the memory compression. So if you do that, again, this is a slide summarizing what you get. So NERF would be a day of work to train a model, 5 megabytes. Direct voxel grid optimization would be 20 minutes optimization, but 0.5 gigabyte of data. Tensor RF would be 20 minutes optimization or something like that. And again, 5 megabytes as internal memory storage, which is very comparable. In fact, in this case, nearly identical to what you get with NERF. Okay. All right, so I think this is a very good place to stop for a minute and also ask if you have questions. Maybe there is a break that needs to be taken. So Yuki, you tell me.
Yeah, how about we take a break for 10 minutes, so until 10 past, and then we can start with questions for the first 5 minutes or so, and then we'll continue on. All right, see you in 10 minutes.
You can still hear me, UK.
Yeah, I can hear you. Could you send us the PDF slides?
I will do that. Yes. Is this? Can anyone hear me or just you?
Everyone can hear you.
Okay. All right. So can I just paste the slides onto the message board here, meeting chat?
Yeah, that should work. I will
Okay.
upload it internally to the course page.
Okay. Yep. Right. Wow. Wait, let me try to compress this a bit. It's 120 megabytes.
Yeah. All right.
PDF.
I mean, I can also do that here with preview.
I should be fine. I have my tricks.
Yeah.
I think. Let's see. Let's see whether this is actually true. Yep. Yeah, it went down a factor of 10.
Oh, wow.
It's interesting. Yeah, interesting. Yes. So next part will be a bit more advanced. So this was a little bit introductory.
Yeah, yeah.
I hope this is fine.
I think it's good. I think the break will help. I mean, the students had like already 2 hours of lecture before that today, so that's a bit the set point, but should be good.
Okay, very well. So you tell me when to start again.
Yes, let's say 10 past basically. Yeah, and I will come back here as well. I'm just gonna upload this now. Might grab a coffee actually as well. So.
Yep. Okay. And I have time till when?
Ideally, let's say probably 2:50 past. So the students have like, because it's such a tough day, they like after this lecture they have 2 more hours of tutorials basically. So if they have like 10 or even 15 minutes break before that, it's pretty good.
Okay, fine. I'll keep it short.
Thanks.
Well. Well, no. Let me just simplify things a bit. Skip this. Okay. So you have taught self-supervised learning, right?
No, that's coming next week, basically. So next week will be self-supervised learning and multimodal learning.
I see.
I mean, I've already mentioned and teased about it a couple of times, but the proper lecture will be next week.
I see. Okay, I'm just gonna simplify things a bit then, in the interest of time.
All right, I'll be back in 5 minutes or so.
Mm-hmm.
Andrea, are you back? Or here?
Yeah, of course.
All right, cool. So I would say let's maybe have 5 minutes of initial questions, and then we'll have the rest of the questions later. I'll ask perhaps first in the lecture hall, are there any questions? Yeah?
Near the beginning.
Yep. Beginning how, do you know the slide number by any chance?
Okay. Oh. Can you hear me?
Vaguely. A little bit.
So near the beginning of the lecture, you mentioned implementing symmetries. And you mentioned a trick, I think slide 12 or so.
Slide 12.
You mentioned that this flipping mechanism, or sorry,
yes,
is better, perhaps in this case, but is better than implementing it directly.
Yep. So the main reason is that you don't need to. So if the obvious alternative to try to, so there are two alternatives. One is to make this exactly symmetric, all right? So you can force that as hard constraint, but that is not ideal because you want to allow it a little bit of flexibility to actually break the constraint when needed a little bit, okay? Two, the other thing you could do here is to have a loss term that says, okay, take the depth map, flip it left to right, and compare it to itself, and make this distance, L2 distance between the results, the resulting difference small enough. Now, that can work, but effectively that maps to an additional term in your energy function. So now you have the main energy function you want to optimize, which is the reconstruction loss, yeah? And then you would have another energy term, which is the one implementing the constraint. Now you have to balance these two things, which is possible again, but it's annoying because you have one parameter, which is the weighting between these two factors, and you need to figure out. So if you do it this way, then you need to add any additional term, and it just encourages the property you require without having to modify your energy in any way or your loss in any way.
All right, cool, thank you. Any other question? Yeah, hang on. Can you? Yeah.
Thank you. Hi, Andrea.
Hi.
This is Vedaldi, and I wanted to ask why NERF model is thin conditioned and the model trained on one thing cannot generalize to another thing. And what will happen if we train on multiple things?
Yes. So I think this is about NERF, isn't it?
Yeah, on about NERF.
Yeah, so this is what we're going to discuss in the next hour. So good point.
So then that's the perfect bridge to I think to the next part of the lecture, and then we'll have another Q&A session for the remaining questions, I would say.
Yes. Okay, so moving quickly here. So we have seen NERF, and based on the comment, the question just now is absolutely true. So NERF is good in many ways, but it only does one object at a time. Okay, so you optimize one NERF model for one object specifically. So here are a few NERF results. So these are the ones I showed you before. Those were were obtained using tensor RF. Okay, and they look great, but just let's look at how much training data is needed to be able to do that. So these are the training images that are used for the toy tractor, the Lego toy. All right. So you need to use those images and these images as well. All right. Now combine all these training images. So these are extracted from ground truth. These are true views. All right. Combine them into optimization, and you learn a NERF model that is then able to reconstruct the object with a high fidelity. But of course, you need lots of data, and you're learning one object. Okay. So in other words, NERF has a terrible statistical efficiency. So that's a downside. It's not designed to be statistically efficient. What does it mean to be statistically efficient? It means to get the output you want with the least amount of data possible, all right? So NERF assumes that you have dozens of views of an object. For example, this is a real object reconstructed using NERF. So in this case, the input is a video of the object seen from all possible viewpoints. That video will have hundreds, if not thousands of video frames. You combine them, you get a reconstruction, yes. But then again, you know, it's not that hard in terms of generalization, or the statistical efficiency is very low. Now, next part is going to be about improving the statistical efficiency of NERF. Again, plenty of things you can do. I'm going to just describe a few. So that's the situation, right? So you can plot this into a diagram. So we have the amount of prior knowledge, which is in your network, like how much the network knows about the three-dimensional world and geometry in general, and how many input data you need to provide for reconstructing one object. So if your network knows very little, then you probably need to pass in hundreds of views for one object to reconstruct it. And this is what NERF does, because when NERF is trained, your MLP or your tensor table or tensors, they start from scratch. They start from random initialization. All right. For each object, you start from scratch. There is essentially almost no information in the network when you start. Everything has to be acquired from data for that specific object. So you need a lot of data for one object. What we would like to be, where we would like to be instead is displayed here in the diagram, where we only need maybe one view or maybe a small number of views for one object you want to reconstruct, because there is a lot of prior knowledge about those objects in the model already. Okay, so that's what we want to get. We want to get to a model that already knows about geometry, already knows about the world, so you can solve geometry-related tasks like reconstruction in a more statistically efficient manner from less data. So where are you going to get the data which is required to train this prior that once trained allows you to do this reconstruction efficiently? Well, you need training data to train that in the first place. And it's not so easy because you need multiple view data to do this easily enough, all right? So you can try to train this from the internet. We're going to see a few examples later about doing just that. But generally speaking, if you have either 3D data directly, like 3D models, that's the easiest probably. Second best thing you can get is multiple views of the same object, in which case learning standard NERF is actually relatively easy. And from that, you can learn your prior, okay? So what we're gonna do now is we're gonna seek a way of obtaining large quantities of multi-view data so you can learn about objects that exist in nature and build this prior models of data geometry and appearance. So what we did was introduce this data set, which is called Co3D. That's a paper in CVPR last year. And this year we have released the version 2 of this, which is just better and larger. That's a piece of work that was done in Meta. So what we've done here was to task Mechanical Turkers, so folks in Amazon Mechanical Turk, to go out there with their cell phones and capture objects by flying around, going around them, right, with their cell phones, and uploading this data, these data sets, these videos up to our servers. Of course, yeah. So you pay for them, but because these are not, this is just amateur, they're not professional photographers or anything like that. Actually, that cost about $1 or so to get a video, and it's easy to get a large number of them. So you got about 50,000 of them. I believe now the number is even larger, and in fact, quite a bit larger. And hopefully next year is going to be larger still. All right. So what do we do with this data? So this data essentially consists of these videos, again, that show the object from all different sides. So we call them turntable-like videos, although there is no actual turntable. We reconstruct cameras, and in the data set, you're going to get the videos together with information about where the camera is, or what is the viewpoint of each object in each split frame in the video. Okay, and with that, well, you have just enough data to be able to train, if you like, a NERF model for each one of those thousands and thousands of videos. Okay, but we don't want to do that. What we want to do, you can do it, and that's also a problem which is defined in the Co3D benchmark, in case you're interested. But the reason why we were motivated in collecting this data was to go beyond that. So what we want to do is we want to take our training video, for example, for a specific category, like a fire hydrant, okay? We want to use them to train a model, and then this model at test time should be able to take a small number of views of a new fire hydrant, maybe 1, maybe 3, 10 views, something like that, and reconstruct a good looking reconstruction of the entire object. By using what? By using the information which is given at test time, which is just a small number of views, plus whatever has been learned about fire hydrants in general from the rest of the data set. Okay, so that's what we want to achieve. New view synthesis from a small number of views. So I'm going to introduce one method that does that. So this is how we solve the problem with a method which is called WC. Okay. So here we have two views as input. And from those we extract features, for example, using a ResNet encoder. Now there is a third view that we want to reconstruct, like so. We should raise, as we would do for standard nerve. And for each one of those three-dimensional points, we need to get the occupancy and need to get the color. So to do that, what we do is we're going to find the projection of those three-dimensional points onto the views. We're going to take the ResNet features that are being computed there, like these are 2D features, we pull them, we combine them in a way which depends on the geometry, on the angles of that these rays forms with your viewing direction. We have a certain aggregation function that could be as simple as an MLP, and that is going to be mapped to what we require, which is the color and the occupancy or absorption coefficient. And with that information, then we can render our target image. So this is how this works. This is called WC, which stands for word conditional embeddings. And is also similar to a bunch of other works, primarily Pixel Nerve. These works, they all came out basically the same conference. The most famous one, I think, at the moment is Pixel Nerve. Okay, that's the idea. So essentially, you do the nerve thing by casting rays and measuring color and occupancy at different location in space. And to get those values, you pull on the fly the other views to try to reconstruct what those values should be. And crucially, the MLP that does the combination, okay, as well as the features here, the ResNet features and that you pull, they are fine-tuned from the Code3D data set to do a better job at reconstructing object from a small number of views as possible, okay? And here you can see some results of this method, WC, combined with NERF and another network here, which is called Scene Representation Network. So NERF is not the only specific model that can be used for the purpose of 3D reconstruction. There are others which are related. And so if you try to do the reconstruction from a small number of views without using this trick of using the word conditional embeddings, then it would just wouldn't work. You wouldn't get nothing out or almost nothing. But with that, you can, from a small number, I think this is up to 10 views, reconstruct reasonably good reconstruction of your objects, which are kind of blurry still. These things are getting better by the day, by the way, but they're better than complete noise, all right? And there is a third thing here, which is called Nerd-Fortner. That is the combination of the WC idea with a transformer network, okay, in which the pooling is not done by MLPs any longer, is done by using a transformer, which pulls information along rays and across different views, all right? So you can look this up later if you want. And that gives you better results still because it's a more powerful network architecture. And here you can see some more examples. And generally speaking, Nerd-Fortner is what gives you the best quality results. And this is not quite state of the art. This came out last year. This year, these things are improved already. A lot of people have followed the template of Nerd-Fortner and they use transformer to pull information now. And yeah, so at ECCV, well, challenge coming at ECCV, challenge came at ECCV this year. So this is done now. But the dataset, the version 2 of the dataset is out there. The leaderboard is out there. So if you want to enter the challenge virtually, at least you can. And you can report results in your paper against prior baselines if you're interested in this sort of problems, okay? And you have, okay, no, sorry, you have 40,000 videos in this case, and more will come later. Now, the next thing I want to discuss is moving beyond just this task of reconstructing the geometry of an object and start to discuss how we can get back a little bit of semantic into the story, all right? So what I want to do here is instead of just getting the 3D shape of an object, I want to use that 3D geometry, 3D shape, to also reason about the meaning of what is seen in the image, okay? That's what I'm gonna try to do in the next part. And for that, I'm gonna use something that you're gonna probably see in the next few lectures, but I'm gonna give you a very quick preview. So I'm gonna use, first of all, a visual transformer, which is, you probably, I'm not sure whether you've seen that or not, maybe you can tell me, but essentially it's a transformer network which is designed to process images. And essentially this is what is replacing convolutional neural networks for the processing of visual data now. They're more expensive than CNNs, but they tend to work better, particularly when you have tons of training data to learn them from, okay? So you can think of this as a CNN. It is not, it's a vision transformer. Essentially it's a network which is optimized for computer vision application which in this case happens to be based on a transformer architecture, okay? So this is going to be a network that extracts information from 2D images only, okay? What you're going to do is you're going to take this model and self-supervise it. Now, this slide you cannot understand, but you're going to understand it after Yuki teaches you about this method, when there's going to be the time. But essentially, this is to say that with this machinery here that I'm going to discuss, you can take this model, you can take a data set of 2D images, which are basically random, all right? And let this thing turn numbers for a while. And eventually, the result of that is going to be a pre-trained architecture, pre-trained weights for your transformer or potentially your CNN. And those weights will actually be very useful. So why useful? Well, this is the result that you get by this feature using this dyno method, okay? So the vision transformer that has been trained on a random collection of images, I think, well, basically something like ImageNet, all right? Without using any human label. So this is completely unlabeled. And what you see there is a video, which has been, so the authors have been feeding each one of these frames independently to your network. And what you see visualized to the top right there are heat maps, which are computed within the model. It's just a way of visualizing which features have been learned. And you can see that they light up the monkey. What's going on here is that automatically, in some sense, this model, without supervision, has trained features which tend to be selective for specific objects in images, although this was done without labels, which is amazing, okay? This is actually an amazing result. And again, Yuki is going to teach you more about this later. But suppose we have that. So we have a 2D model. In this case, it's going to be a pre-trained model, all right? That knows about semantics, either because it was a supervised model or because it was an unsupervised model of this kind. And I want to use it together with 3D geometry to do something useful with it. So what we're going to do is we're going to introduce this idea of neural feature fusion fields, or N3F or NEF for short. Okay, so what this does is it takes this 2D network that operates on a single image at a time and extracts some generic features for that image. It takes this idea of reconstructing a model using NERF and fuses them. Okay, what does that mean? So we have seen NERF already. So NERF is this model that has two functions, the absorption and the color, right? And with that, you can render an image by casting this ray, and for each one of the 3D points, you just simply evaluate the MLP to get the color and occupancy of that point. Same as usual. So you have an MLP that takes the 3D point, codes that up using spatial encoding, does some number crunching, and spits out the color and occupancy. You get a training sample, which is just an RGB image. You compare that to the image which is produced by NERF. You minimize that loss, and that allows you to train the NERF model here, the MLP. Okay, that's what we've seen in the previous part of the lecture today. What we do now is we extend this so that in addition to the training image here, we pre-filter the image by extracting these features. Again, could be the dyno features I've discussed. It could be some other kind of features extracted from a supervised network. It doesn't matter. It works for anything. What you get here is essentially a feature-like or feature image. So it's an image, generally at a lower resolution than the input image for computational reasons, that at each pixel attaches not the RGB color, but attaches a bunch of numbers, say 200 numbers or something like that. Those numbers happen to be features that is ideally capture, for example, something useful like the semantic of the pixel, the meaning of the pixel. So what we do is we extend NERF to have another head. In addition to producing the color, this head also produces or predicts the features, all right? So basically we learn to render not just the RGB colors, but also the feature image. That's the idea. And now by training this model, now what we do is we are fusing inside the MLP, not just RGB information, but also information that comes from these features. All right? So what do we do with it? What can you do with that? So here are some NERF-like reconstructions from image sequences, and they look amazing as usual. That's usually the case with NERF. But what we do is we also learn these features together with the images. So now what we can do is we can say click points or select a patch in the input image, take the features for that patch. These are just 2D information. But now because we also have features which are being fused into the 3D model, we can grab them. We can compare the features in the image with the features in the 3D model and select the object. Okay, that means that we can segment the object out in 3D directly, completely automated in a completely automated fashion. There is no supervision for the features. There is no supervision other than the multiple images for the 3D model. You get a 3D model, which is now also selectable. It means decomposes into different parts, which is really nice, really nice. And so you can see here, just to convince yourself that it's actually 3D, you can see that we have decomposed the scene into the foreground and the background, the flower and the leaves. Okay. This is another example of this working. In this case, on an egocentric video. So the video here to the left is the input. It's very complicated. It's very confusing because the camera viewpoint is changing all the times. But if you can do a 3D reconstruction, then the geometry, for the most part, does not change because it's just background. And then NeRF is very useful to reason about that static background. Can also be used for dynamic foreground. And I'm going to show you that today. But mostly, think about the static background for now. So you can extract dyno features or whatever other kind of 2D features I have. These are visualized here using PCA, so reduced to 3 dimensions, so you can visualize them as colors. And you can see them here extracted from each frame independently using the original feature extractor. And here they are predicted using this NeRF-like model. Okay, these are reconstructed feature from the 3D model, which has been learned. And what you can see is that they high resolution, just because NeRF has infinite resolution, in fact. So you get an interpolation effect, but most importantly, you get a stabilization effect. So these features, they are estimated from each image independently. They should be view invariant, but they're not exactly. That's a limitation of the network. But if you fuse them in a coherent 3D model, then you can remove a lot of that variability. So what you can do with it is, for example, select objects again in a manner which is more stable. So here we have selected a cheese grater. It's a little bit difficult to see in this video, but you can see that there are some red patches. The red patches are the ones which are close enough to in feature space to the features of the cheese grater, okay? And you can see that there are some here as well, where, the cheese grater is to the right. So you should only see red here, but actually you see red a little bit everywhere, okay? This is because the feature is not all that view invariant, but if you fuse them, then they become very, very stable, okay? So they really select for that object in all the frames. And in fact, if you use this for object detection or for object tracking, then using the dyno features or the 2D features directly, could be dyno features, could be Mock V3, which is another self-supervised feature extractor or date, then if you use them raw, you get a certain level of performance in object detection. If you fuse them, you stabilize them using a 3D model, then everything jumps up. So this is a clear example where 3D geometry is very useful in improving 2D semantics, making that more stable, more consistent with respect to the viewpoint. And then you have other applications. For example, scene editing. Here we have a packet of something, and we can select it and say, okay, take this away, and we can reconstruct the scene without. So this is with the object, so you see the packet here, and here you see that it's gone, all right? Again, using this ability of selecting 3-dimensional structure in the image. Okay. I'm going to show you 2 more things a little bit quickly that I hope are going to be inspiring. It's going to be probably a little bit too fast to be very clear on the details, but they're just interesting, I think. Really this pushes still the art for what you can do with the representation as of today, I think. So what we're going to try to do now is reconstruct a cat. Okay. Now, cats are the bane of computer vision. So there are 2 hard things in vision historically: chairs and cats. Okay, chairs because they're defined by function, not by shape. So it's very difficult for a computer vision system to understand what is a chair, because chair is anything you can sit on, all right? Cats because, well, they're not as variable as chairs, but they're very deformable. So reconstructing them in 3D has been, so far, a tremendous challenge. So what we're gonna do is we're gonna take a bunch of videos of the same cat. So we're gonna do co-reconstruction of a cat in multiple videos. Without supervision, we're going to try to get, or almost without supervision, we're going to try to get an animated 3D model of the cat, which has a bunch of control points that allow you to express the deformation of the cat in different frames of the video. So these are a preview of the results we're going to see. So we can take those videos, we can get approximation of the 3D surface. And for you can also see that there are some colors attached to the surface. Those colors are in correspondence with different semantic parts of the cat. For example, the legs, the head, the tail, etc. All right. And we do this by optimizing a NeRF-like model, which is animated on all the videos we have of that one cat. All right. That's what we're going to do. Now, I said we want to do this without supervision, but we cannot quite get there yet. So what we do is we use supervision for pre-training some networks that help us to get there. So what we do is we use two kinds of networks in particular. So we're going to use, we're going to use the RGB images, which are just the video frames. We're going to use an optical flow network that gives us correspondence between different frames. That's pre-trained. It's 2D network, by the way. There is no 3D yet. And we also get masks and appearance features. So the masks, though, are just the 2D mask of the object that we get with something like mask RCNN, if you've seen this before. All right. So we get 2D features, we get the 2D videos, and we also get these 2D outputs from pre-trained networks, the flow and the masks. And from that, we combine them together. What we get out is the canonical model, so sort of average shape of the cat. We get the deformation of the cat in each frame, and we get also the camera viewpoint in an automated fashion. So what are the ingredients for doing that? Well, so first of all, we get a canonical representation, which is, again, an implicit function defined more or less like nerf. So there's going to be an occupancy, it's going to be a color that defines the pose and shape of the cat at rest, okay? And we have a bunch of Gaussian bones. These are basically control points which have a Gaussian influence in the local regional space, which can drag along your reconstruction, if you like, to deform it and animate it as needed. And then again, so we have these pre-chain correspondences, which are of two kinds. We have the optical flow network, and we have dense pose. You probably have not seen dense pose yet, but that's a way of labeling each point of an object with a semantic label, which tells you which part it is. But instead of being done in a discrete manner, saying this is the paw of the cat, is done in a more continuous manner. But effectively, this is again 2D information. So the canonical shape of the cat is defined in an implicit function by having a occupancy function, just like in NERF, or the absorption function like in NERF. This is not an occupancy though, it's an SDF based, so it's a sign distance function. Essentially the same story, it's just a slightly different mathematical definition what the function should be. Well, not slightly different, it's different, but basically you get the surface as a level set of a three-dimensional function, as you would get if this was actually the absorption using NERF. We also get for each three-dimensional point a color, and we get a version of this canonical embedding, which is this dense pose encoding for the name of the part, if you like. All right. This is similar to NEF, and we're going to do this again in the last part of the talk. So for each point in space, we're going to estimate a color, an occupancy, as well as a feature vector. That feature vector somehow captures some information about the 2D image, which in this case happens to be continuous correspondences coded up by this method, which is called dense pose. When we shoot an array to render our cat, you're going to notice that the cat is deformed usually. So what we need to do in order to render the cat as if this was NERF is to undo the effect of the deformation. So the deformation is established by these control points that can drag the shape along in a sort of semi-elastic manner. So what we do when we shoot the array is we take all these 3D points, we map them back onto the canonical model where the actual shape and color of the cat are defined. Why do we do that? Because this is the invariant through time, and this one changes through time. So in other words, this is a way of factoring what changes, which is deformation, and keeping the rest invariant so you can actually learn it properly, okay? But the net result of that is that what was originally a straight ray through your scene, now because of this effect of undoing the deformation becomes a sort of curvilinear path in the canonical space to account for the deformation of the object, okay? And again, this is obtained using these Gaussian bones. So you can see here a sort of animation that illustrates what happens when you use these bones to deform your mesh. Okay. So we have pre-trained optical flow, means that for each pair of frame, we have these arrows that tell us which pixels corresponds to which pixel, again, from a pre-trained network. And we make sure that whatever our 3D model predicts in terms of 2D correspondences matches what is suggested should be the correct match by the optical flow network. And we have this dense pose network that for each pixel in our image gives us a color coding for the particular part of the object seen at that point. So, pink here would be paw and green here would be tail. And then we match these colors, which really are just n-dimensional vectors in practice, to the corresponding colors of pseudo-colors or feature vectors that we estimate from the 3D model in a very similar manner to what I showed you before for NEF. these ones, instead of being dino features, now they happen to be dense pose features. But it's essentially the same idea, except that now the features are optimized specifically for coding different parts of an object, as opposed to be generic features. Combine this together, what you can see is that we have different views of the object, and they're in correct correspondence with the model. So you see here the back of the cat, mouse, the back of, oh, sorry, this is animated. It's hard to point, but so you can see this part of the cat maps correctly to this part of the cat, etc. So it shows you a little bit the correspondence which are established between 3D model and 2D images, and they look reasonable. And then you get results. So it works for cats, works also for other objects. So penguin, that's a dog, I think, also for humans. If you have multiple views calibrated, it works better, but it can also work from monocular. Usually, they run this on monocular videos, okay, which are not synchronized. It means that they are taken at different times. And yeah, so here you see more of the same. So you see the underlying 3D model with the color and the texture that has been trained. And yes, so then if this is fitted to the video, so if the cat walks, then your reconstruction also works in a similar manner. But you can see that the reconstruction follows the actual cat relatively in a faithful manner. Given that there is basically no 3D supervision at all, this was super hard to get actually. So it was a bit of an heroic effort by the student that did this. And once you have this model, you can play with it. So for example, you can take the texture from one cat and transfer it to another cat. So you get all these scattered animates like the source one, but they all have different appearances. Okay, so this is Balmo. This is CVPR this year. I'm going to show the greatest and the latest. This is something that just came out on Archive, which is even harder task, I think. All right. And this is another heroic effort for a different student that just happened to graduate yesterday, which is Shangze. He's also the same author of the paper that we showed at the beginning of the presentation. So it's coming full circle, that did the 3D reconstruction of faces. This is the same idea, but applied to the construction of articulated objects, which are much, much harder than faces, okay? The idea is going to be similar, but they're going to incorporate what we learned in the past 2 years to try to get to this next level of performance and generality. So we get here, so this is an archive if you're interested. So what we get as input are a bunch of essentially random images of an object. Before it was cat faces or human faces, now it's just horses or giraffes or cows, okay? So they're articulated. These are not videos, so we do not observe the animation. There is no animation to observe. There's just random still images from the internet. What we do is we train a network that at test time can take a single image of a real horse or even just a drawing, and it can reconstruct the articulated shape of that horse together with the texture. And once you have it, you can also transfer an animation from some other video that you got, and it's gonna give an animation of the horse, a little bit like the Banmo example I just showed you a minute ago. Okay, this is what we're gonna do. All right, one fundamental trick was to yet again combine self-supervised 2D learning with 3D geometry. I think you're gonna see more and more of this year. People using 2D supervised networks, diffusion models in particular, to aid the learning of 3D models. Now, this does not do quite that yet, but it's still using these dino features, which are self-supervised. These are the ones that I used before for NEF. A good property of these features is that not only they tend to correspond to different objects very well, characterize different objects very well, they also tend to characterize different object parts very well. So you can see here to the right, the dino features, unsupervised, all right, that fire on different parts of the horse. So the leg are green, the tail and the head are purple, and the body is yellow, okay? Again, this is unsupervised, but it's crucial because it tells you a little bit about which pixel correspond to which part of your object. And if you can use that in training, that can provide a lot of useful supervision for what your object actually looks like, or for what is the geometry of the underlying object by establishing correspondences for you, or at least helping you to establish correspondences. So that's one main trick. The other good trick that we need to figure out to do this successfully was to control the flexibility of the 3D shape model for the object. It must be flexible enough to capture articulated shapes, but not too flexible because this is unsupervised. And if it is not well regularized, it's going to give you a solution which is just nonsensical. So what we needed to do was to find a 3D representation which was the right trade-off between NERF, which is fully general and can model very complex geometry, but is also very slow, and something which is faster, but most importantly, is still flexible without being too flexible, right? And so the solution we found is actually from another paper, is this one. So we use a grid that's similar to direct voxel grid optimization, or even like TensorF, okay? Well, more like direct voxel grid optimization. This is actually a grid. But it's not a rectilinear grid, it's the tetrahedral grid. And you might wonder why they do that. Because then there is an algorithm that can take this and very, very efficiently can pull out a mesh from that. So you had an encoding of your surface with an SDF, a sign distance function, which is tabulated in a grid, which is continuous and is implicit. So that allows you, for example, to change very easily the topology of your object. But for rendering purposes and for processing purposes, you convert that on the fly instantaneously at every iteration of training to a mesh, okay? And that regularizes the solution as well as making the steps of the processing faster. Okay, so you get speed and it controls complexity, all right? And this is essentially fusing meshes with implicit function using this idea of instantaneous conversion between the two representations, okay? That's an idea. The other idea, as I said, is in addition of estimating the shape of the object in the tetrahedral grid, we also store a fused version of these dino features like in NEF, and that's going to help us establishing correspondences implicitly with what we see in the image. We don't actually use key points or anything like that. No, we simply reconstruct these colors, false colors, which are just a visualization of the dino features that are completely unsupervised, okay? So these are the two key ingredients. There is a third one, and then I can show you some results. So we close this, we plug these ideas into essentially what is another new autoencoder architecture. It's very similar to what I showed in the first part of the talk. Same idea, same author, in fact, okay? But with these new extensions. So we take an image, we have an encoder network that produces an albedo, so the color, if you like, a deformation field. This wasn't there because we didn't have deformations before. This is a deformation that tells you how your canonical shape changes. For example, here you see that the tail of the horse and this part of the neck of the horse, because of the hair, have a different shape now. So this network will take your canonical shape and will modify it so that you can adjust for these details. We have an articulation. So we have, I didn't explain this in detail, but we have an automated, semi-automated way of attaching bones to your articulated shape in such a way that you can bend your leg without deforming it in a way which is complete nonsense, okay? We have lighting, so we can get shading. And we have, so this was actually absolutely crucial. So one thing you're gonna learn if you try to solve these problems yourself is that it's very difficult for an unsupervised method to figure out that an object is 3D in the sense of knowing that an object can have different viewpoints on different aspects. Because these different aspects tend to look very different. The front of a horse looks almost like knotting the side of a horse, right? So figuring out the viewpoint before you already have a good understanding of the three-dimensional nature of the object is very hard. So to bootstrap that effectively, we have a way of sampling a certain number of viewpoints during the optimization, but this is also done in a new way. So the way this is done is by proposing at every iteration of training, one possible viewpoint, using a function here that tells you which are the likely one to work for this particular image. And that function is trained essentially by just looking at the reconstruction error without having to try all possible hypotheses for all iterational training. So it's essentially a way of self-supervising this proposal for viewpoints, which allows you to sample effectively multiple viewpoints over time. But for each instance, for each iterational training, you only sample once. So this does not cost you anything, right? So it allows you to sample, explore viewpoints over time, but every time you do an iterational training, this is just as costly as only having one viewpoint at a time. That's another novelty that we have in this piece of work. Okay, this was a lot. That's a complete model. We have this tetrahedral grid that is this hybrid implicit eclipse representation, which unifies as NERF with meshes, if you like. This idea of that gives us the canonical shape of the horse or the animal that we are learning. We have this feature field which reproduces this dino features. We have this autoencoder network that takes the image and modifies the canonical prior mesh to take the detail of the particular horses in the image, as well as the articulation, the lighting, and the texture, and also estimating the viewpoints. And then this is trained in a self-supervised fashion by doing what? Matching the dyno features that you observe in the image, because we're doing this fusion, we're implementing this fusion idea, matching the texture, so the colors, and also matching the mask. We're still assuming that we have a mask, and that we get from mask arsenal. So this is the one last thing that we need to get rid of for this to be completely unsupervised. Okay. All right. And so here are some results, and then that's my last thing, so you can stop. So some horses, you see here the 3D reconstruction that was obtained. Now this should now rotate. It's not perfect, but believe me that just getting the fact that there are different legs that separate, there are lots of prior work that have been trying to do this before. None of them can do this. All right, so still imperfect, but I think is a substantial step forward. Those were the images. As I promised, this tends to work also for illustration. So here we go. Now, this is a very useful test. Again, just as I showed at the beginning of the presentation, I think this kind of test of generalization really suggests whether the model has trained something useful or not, all right? Or, is a good way of testing whether the model is good or not, how well it can generalize. In this case, it can generalize decently, all right? Even to stuff which is fairly out of distribution, like the toy horse here with wheels. Well, I mean, we do not get the wheels back, but, we sort of get something that resembles it. And now this is the phone because, as you can see, it has been animated. And it doesn't work just for horses. It works also for other similar animals. So here we have giraffe, cows, etc. And, it's not perfect. So you can see that the shape is a little bit incorrect, but you still get quite a lot of detail. For example, you get the ears and the horn of the cow. And, the shape of the object overall is definitely the right one. Okay, so for example, the giraffe has this long neck. Okay. And okay, you can also run this on a video where we do this on each frame independently. So this is just to show that the results are relatively stable over time, even though there is no effort to actually make them so. This only depends on the fact that the model itself is relatively stable, all right? And yeah, so that's all I have. Oh yeah, no, final teaser here. So this is a 3D printout of the horse, so you can have fun once you have the model. Try to reconstruct the horse in real life. It's not an Earth, it's just an actual video of a bonsai tree in our lab. Okay, now to conclude. So I showed you quite a lot of stuff today. I showed you neural rendering, so I gave you an introduction to that. And then I move into learning and scaling this up. So I introduced Code3D, which is the dataset, which is actually quite useful if you want to do research in this space. And then I showed you several applications of neural rendering, 2 different tasks in 3D reconstruction. So I show you the NEF, which is this idea of using 2D features with 3D models. So you can combine the geometry with semantics. And then I show you 2 models that do reconstruction. In one case was a certain number of videos of a cat, reconstruct that one cat in those videos. This is almost like NERF done for a certain number of videos. And then the final model I showed you here is even more general. So this is learning a autoencoder that can reconstruct an object from a single image and is trained from single object or single instances of an object downloaded more or less at random from the internet. Okay, that's all. I think we have 5 minutes for questions. So I'll be happy to answer any you might have.
All right, thanks, Andrea. Let's thank you first. Right, are there any questions here? Otherwise, oh, is there one in the back? No, maybe from the chat, are there any questions? I think people are still digesting the slides, so.
Yeah, I know. We can wait 1 minute, I suppose, but if you have a question in the meantime, I can answer that.
There's one lecture, there's one question from the lecture room online.
Yeah, so maybe less technical question, but what part of, so you're a researcher and you're also a fellow from Meta, and I was wondering, like, what part of this research, why is it necessary that Meta is involved, or not necessary, but like what part does Meta involve in this research? How do they?
So first, yeah, sure. I should say, so I'm also a researcher in the university and a researcher in Meta. So it's not like what we do is conceptually all that different. Of course, there are different parts that are done in different places, but the fundamental nature of the work is research in both cases. Now, in Meta, what we did was to develop, two works are the ones I showed you today in particular from Meta. One is Code3D, and the other one is Banmo. Banmo was a work from an intern, was a PhD student, early this year. And Code3D is an ongoing effort in our team in Meta London. So Code3D is an example of a data set that is more feasible to do in a company than in a university, simply because of the scale of it and the amount of effort it requires. The rest of the work I showed you today is possible to do either in a company or university, if that's your question in terms of scalability. But as we progress with the research and we start to develop what you could call foundational model for 3D, so very large scale models that would develop a 3D understanding of the world, those might be more feasible in a company, just like you wouldn't get GPT-3 done in a university, but you get it in OpenAI, right? So these sort of models for geometry were going to come. They were probably going to come next year, and those might not be entirely feasible in the context of a university. Was this what you were asking?
Yes.
Okay.
All right, then one question from online, Sarah.
Thanks a lot for a great presentation. I wanted to ask about this rendering. If we have some occlusion for images, like if the horse has some occlusion,
yes.
What happens to the rendering?
Yes, this is an excellent question. So these images, they are random but slightly curated in the sense that the horse is clearly visible, so it's not occluded. Okay, so you probably have noticed that. So if the horse, so once you have trained your model, and we do that, we train it with the occlusion augmentation, so it becomes more robust if there is an occlusion. But for training the model in the first place, we are not modeling occlusion explicitly. So this is one thing we were discussing yesterday, how to get the model to work with more in the wild data, where, for example, only the head of the horse is visible. Maybe there is a horse behind a fence or something like that. So this is an unsolved problem yet, but is one which is very much approachable because, well, we have plenty of ways in which we can try to tackle it. One of them is that now there are models that can do a model segmentation of object quite effectively, meaning that it can detect an object and also tell you whether it's a part which is occluded. So if you have that information, then this supervision would be, doing this would be very easy because it would account for the occlusion exactly. Okay. So otherwise, yeah.
Is it possible to use that previous method for excluding the foreground and creating the background and then apply this method to it?
Yes, it's just complicated, but definitely. So the best solution would be to do a holistic reconstruction of the scene and the object jointly, so you can explain all the occlusions which is caused by the background while you reconstruct the object and account for its deformation. Definitely, that's the best way of doing it. Yes.
Thanks.
All right.
If you can. Okay.
Cool. Thanks. Then thanks again, Andrea. And yeah, there's more questions here. So yeah, have a nice evening and speak soon.
Yeah.
Good.
Bye.
Bye.